the next thing I want to talk about is the grouped mutate or the grouped filter. So probably the most common type of grouped operation is the grouped summary, but it can also be useful to do group-wise transformations and group-wise filtering. And so for an example, you might want to create like a z-score within a group. You might want to look at each flight and then kind of rank. You want to z-score its delays to kind of subtract out the variability and the average delay for that flight and the variation in its variability. So sometimes you can do that with sort of a combination of, this is a vector and this is a scalar and this is a scalar, and the mean will be computed per group, and then you just use the regular recycling rules will get you a vector of z-scores. Other times you're going to need to use window functions, which I'm going to explain fairly briefly, and then there's a whole vignette about them. The main thing I think to get from this, even if you don't get into the details, is that the idea of a window function, and sometimes the problems can be solved very easily with window functions that are very hard to solve otherwise. So let's just look at this example, which hopefully I have in here. So first of all, I'm going to create this planes data set, which is just the flights with all the missing delays removed, grouped by plane, and I have done actually a grouped filter here. I've said I want all of the planes to have at least 30 observations. So we look at this data is exactly the same exactly the same columns as the flight data, but now we've just thrown away any planes that flew less than 30 flights. So then what I'm going to do is I'm going to mutate it. I'm going to add a new column, the z delay, which is just the arrival delay minus its average divided by its standard deviation. And because this data is grouped, those averages and standard deviations are computed per group. So we get a z-score per plane, and then I'm going to say, show me all of the planes with a z-score of greater than 5, delay score of greater than 5. That's going to be very, very unusual. It should be very unusual. You can see it's maybe not that unusual. There's 1,000 of them. But now this is sort of standardizing, like this is kind of saying, find me flights that are relatively bad for this plane. They might not be bad overall because this particular plane might be consistently on time, but this allows me to find relatively unusual. Yep.
So the group by function now puts in sort of a virtual vector along with the data set that has the group index.
Exactly. So if you do STR on planes, you'll see there's actually this, well, it's rather, STR doesn't print it up very well. You can see it just looks like a regular data frame, and then there's this attribute, which is this list of indices, which is just for each group, what are the observations in that group. So that's basically all. Group by doesn't really do anything by itself. It just modifies the operation of subsequent verbs, so everything works on a per group basis. Or another way of doing kind of a similar thing is to use a window function, like a ranking function. So these ranks are computed per group, and I'm saying filter out, so I want all of the flights that are in the top 5 least delayed flights for each. Give me the top 5 least delayed flights for each plane. Now, using a filter is kind of, whenever you can use a filter of something complicated, you can always turn that into a mutate. Where you do something complicated and then you look at the result. So you can see this flight for this plane was the 67th least delayed flight for that plane. And then when I filter that, I'm just pulling out all of the ones that have a rank smaller than 5. Or if I want, well, for each plane I wanted the most delayed flight, I could use that. So you can see here I have 1,500 rows, so that's how many planes there are. So windowed functions are a little bit hard to get your head around. I think summary functions are easier to understand. A summary function takes n numbers and gives you one number. Like that's mean and min and median and standard deviation. A window function takes n inputs and gives you n outputs. And there's kind of lots of functions that do that, like addition does that, right? But we're going to ignore all of the functions that kind of work row by row. So a window function is a function that has n inputs and n outputs, but it considers all of the data simultaneously. It can't operate by looking at one row by itself. And so the most useful window functions are those for ranking and ordering things, for doing offset, so say give me the previous observation, or give me the next observation. They also include cumulative aggregates. I'm not going to talk about that today. There's like cumulative sum and cumulative mean and cumulative any, and also rolling aggregates, which dplyr does not currently support, so I'm not going to talk about those either. But I want to talk a little bit more about ranking and ordering. And basically, I'm not going to tell you about it. I'm going to make you look up the differences. So take a look at the documentation. There's these 3 ranking functions. What's the difference? And then if you want to define the 2 most delayed flights, which of those 3 ranking functions should you use and why? So the way that these ranking functions basically differ is in the way that they deal with ties. So if you do min rank, that's kind of the ranking that we normally use, right? That we have 2 people tied for first place, and then someone in 3rd place and someone in 4th place. Dense rank kind of doesn't skip the numbers, right? So you have 2 people tied first place and 1 in 2nd place and 1 in 3rd place. And then row number just ignores ties effectively. It just gives you an ordering, ignoring the particular order within ties. So you basically choose which one of these to use based on how you want to deal with ties. And so if you just want like 2 flights from each plane, then you could use row number. That will give you 2 flights that are the 2 most delayed flights. But if there's a tie, it's just basically going to pick an arbitrary one. It's going to pick the first one, but that doesn't really matter. Whereas if you want to say, well, I want to pick the first 2, and if there's a tie, make sure you give me all of the tied ones as well, then you'd use min rank. And then finally, if you kind of wanted to say, well, I want all of the, if there's ties for first place and ties for 2nd place, I want to see both of those ties, then you would use dense rank. So if we look at these, they're very, very similar. So you can see, if we just ask always for 2 flights, then we get 6,489. If we say include the ties as well, then we get 7,423. If we say include ties for both first place and 2nd place, then we get just a handful more. So, most of the time, I think most of the time min rank is the one you want to use, but depending on the scenario, you might want to use dense rank or row number. Yes?
If we do a range before we do group by, is that order preserved, or is it at the end of group by in the nutshell?
So if we arrange, so there's kind of 2, so if we arrange here, that's sometimes useful. We want to arrange it by plane, so each plane is grouped together visually. That's preserved through the whole pipeline. So if we do that, that's actually quite useful because we see immediately that we've got this guy here.
There is no range.
which has no plane because the flight was cancelled. So if a flight did not fly, then it doesn't have a plane associated with it. So I bet if we looked at that, I bet if we did flights grouped by plane, well, I'm going to use tally, which is just a shortcut for saying summarize the number of observations per group. Kind of surprised that, maybe I should do it like this. Yeah, so there's 795 cancelled flights which don't have planes associated with them. So if you have ordered them already, you can just you don't need to include the variable inside the ranking. It just, inside the row number, or just do it based on the actual position in the rows. Now generally like a range is actually a really expensive operation. Of all of the verbs in dplyr, a range is the only one that has to copy the entire data set. And that's because when you change the order of things, there's no way not to copy. So if you are working with very large data, basically you generally try and avoid using a range whenever you can. And that is one of the reasons that group by doesn't change the ordering of the data, because that's a really expensive operation. Now, the other type of really useful window functions are called lead and lag. They basically give you offsets. And they're really useful if you want to say, what's the change over time? What's the change between this observation and the previous observation? So for example, we might have computed the average delay per day. And now we'd like to say, what is the difference between today and yesterday? Or how has that changed over time? And the easiest way to do that is with lag. So lag is just going to give you the previous observation. But it works, you might have used diff to do this before. Diff takes the difference between subsequent observations. But the problem with diff is it takes an input of n observations and gives you an output of n minus 1 observations. And that's often a pain to work with. So lag always gives you it takes an input of length n and gives you an output of length n. And if you look at the help for it, you can see there's actually an option that allows you to say, well, for the lag of the first observation, what value should that be? And it defaults to missing because you don't know what it is. In some cases, it can be useful to set that to 0 or something else. Now lag also has so by default lag just lags it in the order in which the observations are seen. If your data is not sorted in that way, you can use the order by parameter to say, what I mean by the previous observation is defined by the date. So it doesn't matter what order the dates are in, always show me the observation from the previous date, regardless of whether that is the previous row or the row that's 3 down. So you can do lots of things like this, using this idea. You can say, was there a change? Is this observation different to the previous observation? You can compute percent changes, fold changes. You can do stuff like, was it false before and now it's true? So was the previous observation false and now is X true? So using this using lead and lag can allow you to express quite operations that kind of involve time, like previous or next, in a way that's very difficult to do otherwise. And they take care of kind of making sure you always get a variable of the same length that you had before, which you need when you are mutating, because that has to line up with your existing data. Yep?
Is there an easy syntactic way to make that first value be the mean of the remaining values in the set?
No, not yet. I think that, yeah.
Is that looking for SQL?
Yeah. Yeah, so these window functions basically come from SQL. They're in modern databases, allow you to do similar things. And they're basically, SQL needs them a lot because in SQL databases, there's no notion of ordering. So you can't say what is the next row. In the framework of an SQL database, that makes no sense. The rows have, the order of rows has no meaning. Whereas you can use lag, typically with another variable that says this is the variable that defines the ordering that I care about. And this is really useful in SQL. Okay. Next, I want to talk about verbs that allow you to work with multiple tables. So typically in a data analysis, you don't just have one data frame, you have multiple data frames, and you need to join them together. And kind of the motivation for this is, say, I've created this data frame. I guess I'm using one feature of select I did not mention before, but you can also use select to rename variables as you pick them out. So I'm creating this new data frame called location, which has a column which is the destination, then the name of the airport, and then the latitude and longitude, so the location of every airport. And we might have also done something like this, where we take each flight, we group it by destination, we calculate the average delay, we sort them in decreasing order, and now if you wanted to look at that on the map, you need some way of connecting your delays per airport with the location of the airports. So let's just run this first. So if we do delays, you see there are 116 rows. We've got one row for each airport and the average arrival delay for that airport and how many flights flew into it. If we want to plot this on a map, we're going to need the latitude and the longitude of each airport. We have the latitude and longitude of each airport in this location data frame, and so I'm going to join them together using an inner join function, which I'll talk about in more detail next. And so when I do that, I have the same, well, let's do a left join actually. I'll explain the difference. We have the same 116 airports, but now we also have the name of each airport in its location, and if we don't have a match like ECP, which does not occur in this my locations database for some reason, we just get missing values. So now I have enough information to put this on a map if I want to. And I believe, just to show you, so here I have a point for each airport. They're colored according to the average delay. If it's negative, you get red. If it's positive, you get blue. And if it's close to zero, you get white. So you can kind of see these are dark blue when you're flying to Alaska, right? So maybe there's some correlation between the distance and the average delay. Although you also see like, you know what airport that is? That's Des Moines, I guess, and that's Iowa City, maybe? Anyway, you can kind of plot, but so one thing you're looking when you plot something on a map, right, is you're looking for spatial patterns, and it certainly doesn't seem like there is much of a spatial pattern here. If you looked at this by day, I bet you would see that, or if you even broke it down by season, in the winter you would see more delays along the East Coast compared to the rest of the country. But we need joins because we're often in that situation. You have one table where you've reduced down a lot of data to some useful summary. Now you want to match it up to some other metadata you have.
And the join is implicitly done by the grouping variable, right?
It's actually done, well in this case it is, but that's a coincidence. It's done by the common variables between this and this. We'll talk about that a little bit later. So here's kind of another simple case. We've got two data frames, one which is a list of people and the instrument they play, and we have another one which is the name of each person and whether or not they're in a band. So if we do an inner join, the result only contains rows that match from both of the tables, from both the x and the y. So here we're joining on the name variable. That's the only common variable between these two tables. In SQL terms, that's called a natural join. We're joining based on all of the common variables. If we do a left join, you get all of the columns of x, and if there aren't any matches in y, you get missing values. The other two types of joins that dplyr implements are the semi-join. So the semi-join doesn't add any columns to x. It just says, give me the rows that match y. And then the opposite of that is the anti-join that says, given x, give me all of the rows in x that don't have a match in y. Now there are two other types of SQL joins, the right join and the outer join. The right join is just the opposite of the left join, and the outer join is kind of a combination of two, a left and a right join. Those are not currently implemented in dplyr, basically because they're not that useful, but one day they will be implemented. Okay, so again in summary, an inner join gives you matching rows of x that gives you all the things that match in both x and y. A left join gives you everything in x and all of the matches in y. A semi-join and anti-join don't give you new columns. They just give you either the rows that match or the rows that didn't match. So anti-joins are really useful if you say, well, I have all of this data here. What are the things that don't match in this over here? An anti-join is kind of like a set difference. Like, tell me all the things that don't match.
Is it like an all join
An all join?
that takes that includes all the rows that are either in X or in Y?
So that would be a full join,
Yeah, full join. Okay.
and that does not currently exist, but it will one day. Okay, so to see this again, or another application, let's look at hourly delays. So I showed you this example before. We take the flights, we group it by date and hour, we remove the missing values of the delay. For each hour, we summarize to get the mean delay and the number of flights, then we throw away all the ones that have less than 10 observations. And now, if I wanted to find out whether delays are correlated with weather, I want to join that on to my weather table. So if we look at this weather table, you can see for each date, for each hour, I have the temperature, the dew point, the humidity, pressure, visibility, and so on. So if I join these two together, if I join hourly delay with weather, now I'm going to have something that gives me, which has columns for how delayed each hour was, how many flights there were, and what the weather was. So if I run that and look at it, you can see I have on 7 a.m. the average delay was 5.2 minutes. There were 30 flights. It was 53 degrees. This is Houston in January. The dew point was this, the humidity was that, and so on.
So the weather is indexed by location?
So the weather, yeah, so in this case, all of the flights are departing from Houston, so weather just contains Houston's weather. And this is why you should live in Houston in the winter.
In the winter.
Okay, but now where's the departure delay?
Hadley, what does it default match on if you have multiple?
Oh yeah, so you notice when I do this, when I do a join, it prints out joining by date and hour. So it's saying it's identified the variables that are shared between the two and it joins on those. That's like a reasonable heuristic, but generally to be safe, you'd want to supply that yourself. These are the things I want to join on. And then it doesn't print that because you told it what the right thing is. So generally kind of the philosophy of dplyr is if it's guessing something and it might not be guessing it right, it's going to print it out. And if you want it to hide that message, you basically have to tell it what to do. ggvis has a similar philosophy. So if it has to guess, and that guess is not guaranteed 100% to be correct, it's going to print it out so you see it visually what it's doing. And if you want to suppress that message, you say, these are the variables you should use. So what I want you guys to do is reproduce that data set. So reduce the hourly delays, join it on. You can use the code and the project. And then what I want you to do is try and figure out what weather conditions are associated with delays leaving Houston. And I think using graphics is easiest. Obviously I'll be using ggplot too, but you can use whatever you like to figure that out. So we want to figure out what's the relationship between delays and flights. You know, for some airports, I'm sure there's a strong correlation between the temperature and the likelihood of delays, but as you can see in Houston, there's not much of a relationship because it's never really cold enough. Wind speed, doesn't look like much. Gust speed, not much either. Maybe, so gust speed, there's only a gust speed if there is gusty wind, so you might wonder if maybe having a missing value or not might be kind of predictive there, and it maybe looks like the median delay is slightly higher when the gust speed is missing, which is not what you'd expect if weather had any effect. If you look at condition, which is just kind of a categorical variable, you start to see some patterns emerge. There are definitely some things that are, like if there's heavy thunderstorms and rain, it's, the delays are more likely. Heavy rain or light freezing rain, which it looks like there's only one observation. Freezing rain is not a common occurrence in Houston. But although this still isn't a great explanation, because you can see that even if the sky is clear, there are some really big delays. Now, of course, I think it's impossible to, like the delays, airports are a complicated network, and delays in flights of Houston might be because the flights coming into Houston were delayed, which could be weather several hours ago, or it could be because there's bad weather somewhere else in the country. So looking at this very sort of high level is unlikely to find anything particularly strong, but you can see there's some signal here. Okay, next question, where you're going to have to do the join this time. So are older planes more likely to be delayed? So see if you can answer that question with a plot. Okay, we only have about 10 minutes left, and I realize we have two major topics to cover. But I'm going to just show you very quickly what you might want to do here. So it's always a good idea to just do some basic kind of summaries. Like, this is a little suspicious, right? There aren't many commercial flights served by balloons and engine and so on. And you can look at the distribution, and again, there are some pretty old planes in there. So you might want to look at the ones that are really old and got a number of seats and so on. But then what I've done is I've taken flights, grouped it by plane, summarized it in the standard ways, and this is a little bit out of order. Joined it on with the planes data, then you could plot, do some histograms. I just picked arbitrarily all planes at least 50 flights. This is a plot looking at the average distance flown by that plane versus how much it was delayed. And this one is looking at the year the plane was manufactured on the x-axis and the average delay on the y-axis. Not a huge amount of signal there. One thing, whenever you do match up two data frames, it's always useful to do an anti-join to show what are all the delays that didn't have matching planes. If you look at these, very quickly you'll see there's a common pattern here. All of these plane tail numbers end with either MQ or US, and that's because US Airways and MQ, which I think is Spirit Airways, and for some reason don't report the tail numbers of the planes. They report some kind of internal plane identifier, which means you can't match it up to any other data source. So anti-joins are really helpful for that kind of thing, for figuring out why do these two things not match up. Okay, any questions about that? So now, in 10 minutes, I'm going to give you a very, very quick overview of two other really important topics. I am just going to show them to you, and if you want to learn more, there's more information in the vignettes, and you can refer to these slides. So I've shown you, like, so far you've seen very specific functions. Each verb does one thing, and it does it well. What happens if you want to do a grouped by operation that's not one of those existing verbs? Well, what you can do is use the do function, which is kind of a general workhorse. So it's slower than the specialized functions, but you can do anything you want with it. And if you've used plyr before, do is basically equivalent to dplyr. Now there's two variations of do. You can use it with a named argument, where you give it basically anything. You can put models and so on, or you can use an unnamed version where you give it data frames, and it uses a pronoun, the dot, similar to the way data table uses pronouns to refer to the current group. So here's some kind of code. You can say, like, using this na.last observation carried forward from the zoo package, you can say take this data frame, group it by house, and then for each group apply this function to it. So this function is going to return a data frame, so we're doing this on a group by group basis. We're carrying the last observation forward on a group by group basis. We can also do similar things, but instead of putting data frames in, we can put complicated objects like models in. This creates something a little bit weird. It creates a column of a data frame that is a list. That is a valid R, but a lot of base functions don't support it, so you have to use it a little bit with care. But the thing that's really cool is it makes it very easy to have a column of a data frame that's a rich object, like a model. And in my code here, so for example, what I can do is I'm going to take the flights, look at the flights only in the common hours, and then for each day, I'm going to fit a linear model predicting the departure delay based on the hour of the day. Now this is an absolutely awful model, but it serves to indicate the principle. If you do that, when you print it, you'll see we have a column that's a date, and a column that's an S3 object of class LM, a linear model. Don't do str of it because it prints a huge amount of stuff. But if you just look at the first row, you can see it's basically it's a data frame where one object is a list. We can use all of the regular functions of this. We can use summarize. So here I've created a function that, given a linear model, extracts its R squared. Strange, it worked when I ran it last, but so there's things that are a little bit wonky with this yet with dates because it loses their attribute, but you can say, well, show me which days had the best fit to this model, the highest R squared.
Wow.
Or you can do things like extract all the coefficients from the model and dump them in one data frame so I can do data analysis on that. So do is kind of this workhorse function that allows you to do anything. It ties it into R's modeling capabilities. Okay, that was 5 minutes on do. Now you get 5 minutes on databases. So as well as working with data that fits in memory in R data frames, it also works with data tables and with kind of a fairly beta version of working with data cubes. It can also connect to remote data sources, basically all of the big open source ones, Postgres, MySQL, SQLite, connects to MonadDB and BigQuery, which are columnar data stores. BigQuery is Google's big data engine. And then there's sort of, and the people have submitted various pull requests to make this work with Oracle and SQL Server and ImpalaDB and so on. If you have not used, if your data does not currently live in a database, then the easiest way to learn a little bit about databases is to use R SQLite, because the database is actually embedded inside the R package. There's no setup. It is super, super easy to use. And dplyr provides the copy to function, which allows you to take data out of your data frames and put it into a database. The whole point of dplyr, which I'm basically not even going to show you, I don't think, is that basically, I'll show you a little bit. Basically, you can ignore the fact that your data is in a database and just use all of the functions I've shown you, and they create SQL and do all of the computation in the database and bring the data down to you. So this is the code that I will run this code. Wow. So I'm going to create a new SQLite database. I'm going to copy the data I just created to it, or we've already created. And now what I can do is basically have kind of pointers to that database. So this flights DB object, that's exactly the same as the flights data set we were working with, except it lives in an SQLite database. And anything you can do with locally, well, almost anything you can do locally, you can do remotely. So you can say filter to find all the planes that went to SFO, or do a join to connect the plane information. One thing you'll notice is when you print this out, there's sort of a question mark here. It doesn't know how many rows there will be. That's because when you're working with a database, figuring out how many rows a query returns requires you to execute the complete query, which you don't want to do unless you've specifically asked for it. So everything when you're working with a remote database is lazy. So this code runs instantly, not because it's doing any computation, but because it's not doing any computation. When you actually ask for the results, it will bring them to you. Now there's a few ways to see that. You can use the explain function, which will tell you the SQL query it's going to run. If you're familiar with SQL, you'll notice it creates things in a slightly non-standard way, just basically because I'm not trying to create idiomatic SQL. I'm trying to do my best to convert your R code into SQL code that works. And then it also shows you a query plan, which if you use databases, you should learn about query planners. If you do not know about databases and want to learn databases, I really recommend using these. But this basically is going to tell you, it's the database's prediction for how long this query is going to take to run. Really useful if you're working with big data. You want to know that, hey, this query is going to take 12 hours to run, so maybe you want to do something in the meantime. Very, very quick advice if you do not know how to use SQL. I think if you work with data, understanding SQL is incredibly, incredibly valuable. You don't need to understand all of SQL. What you need to do is you need to know how to write select queries. You need to learn a little bit about how indices work, so you have some kind of mental model for what an index is going to make fast. There's a great reference here. Once you've learned those things, it's useful to understand a little bit more about what select does behind the scenes. Select, you write things in a certain order in select. That is absolutely not the order in which things happen, and it's useful to know about that. And then finally, make friends with an expert. So when should you use data in a database? Basically, the answer is either your data is already in a database, so use that. Otherwise, if your data does not fit in memory, use a database. If your data does fit in memory, it's always going to be faster to use in-memory operations in R, like dplyr or dtable. They are going to be orders of magnitude faster than most databases. Very, very quickly, if you'd like to learn more, dplyr has a series of vignettes which you can access by running browse vignettes. There is a great resource by Jim Hester. If you've used plyr before, it shows you how to convert common plyr idioms to dplyr. And then finally, the Stack Overflow dplyr tag is pretty good. And if you look at the frequently asked questions, that is a good flavor for the things that most people struggle with most commonly in dplyr. Some of those things will get fixed because I didn't think of them before. Some of those things will not get fixed because I think they're a bad idea, but either way, I've normally commented on the Stack Overflow questions so you can figure that out. So that was a whirlwind tour of probably the two most advanced features of dplyr. You don't need them every day. They're really useful to learn about. Check out the vignettes. Thank you.